Hello everyone, thank you for coming to my virtual talk. This talk is about our paper titled Embeddings for Minecraft Processing of Heterogeneous Theory. This work has been done with my co-authors, as you can see in the list. So what is the motivation for our work? As you already know, the information on the web are usually heterogeneous in nature. For example, if you have some music dataset that contain the songs, it may also contain the information such as the lyrics of the song or the audio recording of the song. And we also have additional information such as the composer or also the singer. As you can see in this example, the information we have is of different nature. We have the lyric in textual format. We also have the audio within the audio format. We also have the structured data, which are the composer or the singer, the title of the song. So given this information, we need to have some kind of information retrieval. However, traditional information retrieval system use the unimodal. That means they can only handle one type of data. For example, usually we already have system that retrieval system that can retrieve images or web pages. So our motivation is that we need to have a multimodal or heterogeneous information retrieval system. And the idea of our approach is that we want to model the relationship between the entities as well as citizens. So the entity in this case, as you can see in the previous example, are the songs or the singers or the composers. And we want to model the relationship at the heterogeneous information network. There are two steps in our approach. First, we model the entities and their relationship in a network. Notice in this network, the network is heterogeneous because we have different kind of entities and different kind of relationship. In the second step, we want to capture the distance and the not types and the egg types using a low dimensional embeddings. So that we can, using this embedding, we can perform vector space retrieval. Vector space retrieval is a traditional approach in a traditional information retrieval system. So what is a heterogeneous information network? Heterogeneous information network is a network, as you can see in the reverse symbol, that contain different type of entity and different type of connections. However, the connection between the different nodes and different axes, they need to follow some kind of structure, and these structures are modeled by a heterogeneous schema. So if we have the table of entities, as you can see in the first example, with the songs and the composer and the lyrics, we need to have the table of entities. As you can see in this example, we have the title, the singer, the composer, the lyric, and the audio, and we have different entities here. And for each entity, we can construct a subgraph or a small heterogeneous network follows a heterogeneous schema. So what does this schema do? In this schema define the type of entities, type not in a heterogeneous network, and their possible connection. For example, we have the heterogeneous schema of the song. We contain the entity song, singers, composer, and lyrics. And there are connections between the song and the singer, the song and the composer, and the song and the lyrics. However, there are no connection between the singer and the composer. So based on the heterogeneous schema and the data element, we can construct the subgraph. And as you can see in this example, and if we have many entities, we can construct many subgraphs, and then we can connect the subgraph if they share some common nodes to create a very large information network. And this network can capture the information, the relationship between different entities. After we have constructed the heterogeneous information network, uh, we need to learn a machine learning model to represent the nodes in the graph in a low-dimensional space. And this is the definition of network embedding. So in network embedding, we want to embed a node to an embeddings with either vectors in a dimensional space. However, in our setting, the embedding must satisfy some constraints. The first constraint is the basic constraint of the network embedding. So we want to have a closed node in the network to have closed embedding. And the closeness is defined beyond the unbounded distance and the node time and the X time. And in our setting, we also have the information in some nodes also have the features. So we want network the embeddings of the nodes to capture the node feature. For example, we have the single information or the contents of the song. Then we also want the embedding to capture the node feature in addition to the load closeness of the node and the type of the node and the edges. So there's one approach in network embedding that can satisfy the above constraints. This is called rapid convolution network or CCN. In CCN allows us to capture the node information if we have them. And another benefit of CCN is that we can react embedding for unseen draft. So if we have a new network, so then we can use GCN trained on one network to create node embedding for the unseen networks. However, the problem with traditional GCN is that it cannot take into account the nodes and the X type. So we leverage traditional approach in rapid convolution network to obtain heterogeneous GCN that can take into account the nodes and the X type. The difference between XCCN and GCN is that the information, the model that the model of XCCN can consider the node and the X type by modeling the relationship between them. Based on the model we construct, we can also construct a query embedding. So in order to construct the query embedding, we first need to model the queries at the graph because the query is essentially similar to a data element. And then we can construct the node embeddings for every node in the query graph. And then the query embeddings we define of the node embeddings. So in the experiment, we have from our experiment in different data sets. The first data set, we have the real-world data set, two real-world data set, and one synthetic data set. The real-world data set is a bigger data set. It contains the images, the users, the image groups, and the tags of the image. We also have the DBIS dataset, which is the publication dataset. It contains the paper, information about the papers, the author, and the venues. We also consider a synthetic dataset because we want to able to manage the structure of the graph to test the scalability of our approach. For the query, for each dataset, we construct 100 queries. We decide from 1 to 10. For the metric, we use the normalized discounted cumulative gain, which is the traditional metric for information retrieval. In the first experiment, we use the synthetic dataset to test the scalability of our approach when we change the number of nodes and the number of the density level and also the dimensionalities of the embeddings. As you can see in the figures, as we increase the network size by increasing the number of nodes, the training time also increases. And also by changing the density level, we also increase the training time, the density level increases. The reason for this is that the density, when we increase the density level, we also increase the number of edges in the network. So this makes the size of the network increase as well. For the embedding side, we also observe that if we increase the embedding size, the training time also increases. The reason for this is the embedding size correlated with the number of parameters in the model. So if the number of parameters in the model increases, the training time increases as well. In the second experiment, we want to analyze the effects of the heterogeneous level. We measure by the density level, or we measure by the knot type on our approach in the training time. As you can see in this experiment, as we increase the number of the knot types, the training time also increases. However, the increase is only sublinear, so we can conclude that the training time is more dependent on the number of nodes and the number of edges. In the final experiment, we want to analyze the performance in retrieval of our approach. We compare different embedding techniques, like GCN, XGCN, and not-to-vec. Not-to-vec is a network embedding technique that does not take into account the node features. And in this experiment, we want to analyze the retrieval accuracy using the NDCC metric. As you can see in the figures, we obtain that the XGCN is better than GCN, and GCN is better than not-to-vec on both datasets. We can explain this observation by the following. XGCN is better than GCN because XGCN can take into account the node type and the edge type. On the other hand, GCN is better than not-to-vec because GCN can consider the node feature. In conclusion, in this paper, we propose an information retrieval approach for heterogeneous data, and we propose modeling the data as heterogeneous network so that it can capture the relationship between different data elements. And then we leverage network embedding technique to embed the nodes into a vector space that can be used for the vector-based retrieval. And our experiment on different real-world dataset and synthetic dataset confirm the performance of our proposed approach.